So let's think about what we usually do in Haskell when we have two types that share a common representation. For example, we often have isomorphic types. We want to define inch, which is really shared represented in the bubble. We can do it with new type like that. But when we have something, recursive structure or whatever, that has subtype relation, like expressions of plus, minus, and 4 operators, and the term that only has 2 operators, wouldn't it be nice to do it in Haskell like that syntax, which we don't have? So the motivation is, when we have these two types isomorphic, T and U, we can share the representation and declare T as a new type of U. But we really know that in mind that when we design something that T is a subtype of U, we don't know what to do in Haskell. So we designed a new feature called shared subtype. So this is what shared subtype is about, and we can use this shared subtype when we want to make a subset in a way that either restricting the number of data constructors or ensuring static properties using type indexes. This is mainly related to GADTs. And use efficiency loss. So this is an example of new type that I showed in first. And the important thing is that there's some common operation like equal when there are things that only matters to inch. And then we have code use without conversion overhead, because those data constructor inch, which isn't a really data constructor at runtime, just goes over, and it only leaves the X in line when you use that code. It doesn't have conversion overhead. There can be other way of calling dictionaries, or may or may not be optimized. But so this is the summary of what we've seen. We have some relation on the type level, and we have some relation on the value level. And inch is as kind of isomorphic to double, and whatever inch x is, you can just turn it into x and back and forth. We can do, so let's think about subtyping and what subtyping by refinement means. For example, when we have int type, we can just divide int type into empty lists and non-empty lists, and we can really statically do that by using GADT type, something like this. We'll show you an example in a second. So what is a GADT? Most of you would know, but GADT is a generalized ADT, so we can rewrite any ADT declaration into this GADT form. But we can do more than that, because we can have different type indexes at the return type of each constructors, and have a different range type. We index the veil as empty, and the index the result of the column is fill. And we can construct these kind of values, and notice that they have slightly different types. And let's just think about what the relation this has to the original, this plain old list. When we just cover them up and down the clouds, it really looks like a list, just not very different. So you can think of some relation at the value also. It will correspond to that empty list, and this singleton list corresponds to that old singleton list. And then we have a really similar structure diagram here that says this column has some relation to the value like that, and there's ST that has relation on the type level. So we'll call this subtype rule and show it, and in a moment we'll see that this is a meaningful name. So let's make a comparison. These and new types, for them they are bijections. And we have a language feature that we can realize this idea as a Haskell implementation. But for subtyping with GADTs or just ADTs, we don't have the language feature to realize this concept. And the other difference is that it's in general an injection. maybe not in this case, but in general. So what we do in Haskell, we have two options. First, we can write a conversion function that satisfies those relations. The obvious problem is it can be slow. And if you want to do it in an efficient way, we have to basically redefine many library functions. That is very obvious. So we're really in this situation that, well, we can't go either ways to have both. So I'll just repeat what shared subtype is. We must specify both subtype rule, the type relations, and the value relations. And we have to check the consistency because not all syntax you write down is meaningful. We'll see that in a moment. And we have sharing, and we do it with implicit coercion. And we can form hierarchy like object-oriented languages. And as a result, we have efficient code sharing and library use. So we've seen this picture, and how do we write that and the syntax? So we came up with this syntax, which just reflects this subtype rule and sharing rule just on the code. And how do we use it? We can use this length function for the values of the list, obviously, and we also want to use this like this with the implicit coercion. So this works because we declare it like that. The reason we have to check consistency is that we can do something very silly like this. We want to share cons and nil, and that just doesn't make sense in a different arity. So you have to think about the conditions when that makes sense and how we will check them. So we won't let people write that and go through the type system. So to be a consistent subtype declaration, we have to meet these three conditions. And there shouldn't be a cycle. If the cycle is the same type, there is no need. It's just two different data constructors say both nil and con shouldn't be the same thing. And sharing rules have to be consistent with the subtype rule. I'll explain in the next slide. And this is a restriction in our current work. We're only thinking about this plain data, not the higher order data, which is the function type in the argument or the result type. So what do we mean by sharing rules have to be consistent with the subtype rule? It means that first it has the constructors which are related must have same arities. We've shown that it doesn't. It just doesn't make sense. And also, the types of related constructors sometimes relate some subtype relation. So for example, we made list AE as a shared subtype of list A, and what we want to do when we look at this nil and cons, this piece of syntax, we do two checks. So nil is very obvious, and if we see cons, the type of the cons is in this curly less than subtype relation that, which that means we decompose it until we really see that each of them is subtype. And for arguments, it can be same. We also thought about how to write this for just ADTs, and since term is a subtype of expression, we can just reuse the eval function if we have defined it already. Well, we have a real example here, which we didn't make up. And so this is a paper I just presented yesterday, and when you look at the paper, you have these sigma types and rho types and tau types. But what this really is, the sigma type and rho type is just a partition of the system F type, and the tau type is just a subset of this rho type. And we can write that as some kind of hierarchy diagram, and we can think of the top is the supertype and the below is the subtype. We actually looked into the reference implementation, and you can see that they do a little bit of cheating. It's not because they're bad Haskell programmers, they're really good. It's just that there's a certain itch that we can't point into the current Haskell system, and we can replace if we have this subtype feature like this, and then we really have this static distinction between tiles and rows in sigma, but we can still reuse the type, reuse the functions that define on the system F type, like get all the free variables kind of things by implicit coercion. There are well-known limitations in general about this subtype. You can only go one side from subtype to its parent type or supertype. So we can't really write a map that preserves very precise property that we had in a subtype. So this is, for these kind of functions, we still have to rewrite it. But there's a trade-off between separate compilation. So I'll mention that later. And it turns out that there are many related works. We only look into some of them and noted in the paper. And well, first is Yung Ahn's data type subtyping in Haskell, and the syntax just looks really similar, but in a way, an opposite idea, and didn't cover recursive types or GAT. And in the ML world, there are confinement types, and they are certainly more powerful than this subtyping scheme, but separate compilation is kind of questionable, and there is some advanced version of this called polymorphic variants, which is pretty much related to this, but they do separate compilation, but in a little bit strange way. They hash the value and just hope that they never coincide. So there are some theoretic related works like this. Our rules are kind of special cases of these general work, and there are some more detailed discussions in the paper you can read about. And it turns out that we are reconstructing the subtype definition in an implicit calculus of constructions that has been lost when we come from this calculus to programming languages, because in these kind of calculus, everything, integers and lists, all those constructors are just encoded as lambda terms, and we can really look up the lambda terms and, oh, this lambda term is the same as this lambda term, so this must be a subtype of this. But in programming languages, it's efficient to have the primitive data type constructors, but the users doesn't have a handle to say that this data constructors I want to make it same as this one, or value 0, value 1. So we give that kind of power to the user, and we can have certain efficiency and code-use benefits. So these are some future works. We have to think about the function types, and we made a proof, but there are certain cases that this proof doesn't cover. I can show you at that time. And there are just so many features in Haskell that there's to think about when we put in another feature. One is maybe how would something work with type classes if the superclass type is an instance of EQ? Should we just consider the subtype as an EQ or not? And that's kind of tricky. Yeah, multiple layers of these. And another one is possibility of adopting Haskell features. Haskell actually shares the constructor names, and in often cases we don't want to. If we have 3 different lists, we would really like to when all nil and cons, not something cons 1, cons 2, cons 3. And so we don't have any implementation, we're just in design, so it will be, this implementation will be the feature of 2. And conclusion, the shared subtype is a subtyping by sharing the representation of the actual representation at runtime, as opposed to subtyping OO is like sharing the same interface and dispatching them dynamically. We can use shared subtypes when we want to restrict the number of the constructors, right? For like numeric expressions, we want to have certain operators, or we've seen that we can ensure static properties using type indexes and still share the representation of the underlying like less typed instance. And yes, then so we have library views without efficiency loss. And we have natural separate compilation. This is a trade-off from the limitation that I mentioned. Yeah, and GADT turns to be organized this very well. So that was pretty much all, and thanks to you.
So, in the various subtypes, you have to have different construction names.
Right.
And that's, I can imagine from the point of view of a programmer, indeed in your example, if you want to put up the example of, fortunately, the not bad programmer doing it, you had fun and arrow and air, all
that's
the synonyms.
Right. And
so I can imagine that being quite inconvenient for programmers. I'm sure you must have tried to avoid that.
I agree that that's inconvenient, but sometimes you really want, there are some cases that you want to have different names because we have certain new perspectives of the same data structure. But I agree that there, in most of the cases, it will be inconvenient. So the future.
What did you think about avoiding?
There is a way of avoiding. The Haskell previously really did that. I mean, it's a different setting, but yeah, you can ask. Well, we did, but well, we can think of a syntax like this, and well, see, this for all is duplicated, but since we declared a subtype, we can just use that thing from the down. But when we do it like this, we have to pay something in the other end when we use it, and when the use is kind of and there can be ambiguous context that either we have to specify the type annotation explicitly that I really want to make this as a sigma rather than type data. So the type declaration becomes plain, and then we may have to write some more.
Write more type declarations.
That's
good.
Yeah.
Yeah, use the same constructor names and write more type declarations.
Right, but I think it's still useful to have the user to have freedom to change the names if they really want to. Because there are some cases that you want to view this thing as a whole new thing, but still share the representation. The obvious case is that this kind of finite subset integers, because one of the reviewers pointed out that this is a very special restricted case, but it could be very useful to them. And there are other languages that implement this kind of just only this feature, not generalized shared subtypes.
Any more questions?